In this lecture, we will be looking at a new concept. We will try to determine mechanisms of different reactions using different tools. The first is the linear free energy relationships, and the next will be kinetic isotope effects. So what our goal basically is to determine a reasonable mechanism for different reactions based on experimental results. So this is the first one, linear free energy relationships, also used as LFER. So in this presentation, we will look at structure reactivity relationships. In other words, how does the structure of a molecule change or predict its reactivity? Next, we'll look at the Hammett equation. Hammett, a chemist years ago, made that observation and came up with a relationship, which is called the Hammett equation, to help analyze how change in structure of a reactant affects its reactivity. Then we'll look at substituent constants. From that observation, he developed, or calculated, I should say is a better word, different substituent constants that are used in predicting reaction mechanisms. And lastly, we'll put all of this information together and see if we can use LFER to predict the reaction mechanisms of different reactions. Okay, so let's start. Let's look at these two reactions here. It's the ester, this of course is an ester right here, and an OH, so it's the ester hydrolysis in a basic medium, a very basic reaction in organic chemistry. Hydrolysis of an ester can take place under acidic conditions or under basic conditions. But let's look at this one. This is the ester right here, and in a basic medium, we of course get the salt, the carboxylate salt, and of course the alcohol. These two molecules, they are the same ester, except the substituent back here. One has a nitro group and the other one has an OCH3 group. But notice though, even though the type reaction is the same, this reaction is much slower than this reaction. So the question now is why? So once again, this is the rate constant for the hydrolysis. This is very fast with the nitro group compared to the ester with the methoxy group. The question now is why? But the main thing is the observation that a nitro group speeds up the reaction, and a methoxy group slows down the reaction. Let's see if we can use that information to help us in our analysis of structural effects on reactivities of molecules. So let's look at the actual mechanism here that we've seen before. We know here that the OH, negative nucleophilic OH, attacks this carbon here because it is partially positive. It's electrophilic. And of course, it pushes the electrons onto the oxygen. So this step here is known as the rate determining step. As you will recall, it's the slowest step of a reaction mechanism. The other steps are fast. But this is the slowest step, the rate determining step. This step determines the overall rate of the reaction. So with this OH coming in here, it forms this tetrahedral intermediate here. I should point out here that this nitro group here is making this carbon here even more positive than if it were not there. We'll see that in a second. But the main point is the mechanism involves the nucleophilic basic OH nucleophile attacking this carbon because it is electrophilic. And note again that this nitro group here is pulling electrons from the ring, making it even more electrophilic. Of course, I think you see where this is going. It will make this step here much easier compared to the next one. Let's see. This, on the other hand, it's an electron releasing group or electron donating group here. So these electrons here are pushing into the ring, making this carbon here, even though it's electrophilic, but not as electrophilic as the previous one where it was a nitro group. So as you can see here, this rate determining step here is not as favorable because this OH is attacking a carbon here that is electrophilic, but because this is an electron donating group, it is donating electrons to this carbon, making it less electrophilic and making it a slower reaction for the RDS. Of course, as I mentioned earlier, these steps are the fast steps. So this is the most important step of the reaction that really determines the overall rate of this reaction. So, Hammett made that observation and he recognized that different substituents affects the rates of reactions differently. So what he did, he came up with a very simple reaction. Here, this is benzoic acid and substituted benzoic acid. And he measured the equilibrium constant of different benzoic acid, of different substituted benzoic acid. So for example, H would be benzoic acid. Then he would put a methoxy group back here and measure that rate constant, and nitro group, measure that equilibrium constant, I should say. This is KEQ this time, equilibrium constant, and of course different substituents back here and determine the equilibrium constants. So what he had is a bunch of equilibrium constants for different substituted benzoic acids. He then developed an equation, and here is the equation. Log Kx, which would be the equilibrium constant for a substituted benzoic acid, for example, p-methoxy benzoic acid, divided by the equilibrium constant for just benzoic acid, just H, all 5 hydrogens on that carbon for the phenyl ring. That is equal to rho sigma x plus a constant. Let's define this. This is the slope, and this is a constant. So as you will recall from your general algebra course, this is really the equation for a straight line. It's a straight line where this is the slope and a variable here, and of course the intercept is right here. So this is the equation that he developed. Here's the key though, is that for benzoic acid, he made this slope here 1. So it's plus 1 for the slope. He knew the equilibrium constant Kx because that was measured, and of course Kh, that was measured, so that is known. This is known because he made it plus 1, so he tried to calculate here sigma x for each substituent that's on that ring. Here's what he got. So here's the equation again. This is the equation again here, where this is the slope and this is the constant, sigma rho. This rho here is the slope, and sigma here is the constant. So what he did here is this. So this would be P amino benzoic acid, and the constant for P amino group is 0.57, negative 0.57. And of course, if it's in the meta position, it's 0.09. So let's go down the column here. So this is the OCH3. Notice this is electron donating, and it has a value of negative 0.38. This is also electron donating because it has a pair of electrons on the nitrogen. OCH3, here's the methoxy. Electron donating again, negative. Notice electron donating groups tend to be negative. And of course here we have CH3, negative 0.15, even though the CH3 here does not have a pair of electrons on the carbon, but you will recall that it is electron donating because alkyl groups can in fact stabilize a carbocation. So alkyl groups are considered to be electron donating, and that's why it's negative. Hydrogen, of course, is the standard, so it's assigned 0. Fluorine, all these groups here are electron withdrawing groups, so that's why it's positive. So these groups are electron donating groups, and these groups are electron withdrawing groups here. Just want to emphasize here the magnitude and the sign. So a substituent with a negative sign is electron donating. If it has a large value, it is donating or has the potential to donate electrons to the ring and onto the reaction site. So this is a better electron donating group than this group, for example. Okay, because there is the possibility of meta-substituent versus para-substituent, we also have here other constants for the same substituent but in a different position of the ring. Just to refresh your memory, here we have the benzene ring and we have some point of reference. This is the para position and this is the meta position here. So that's why we have sigma M and sigma P. So what that means is that he got a slope for this equation here. So this is right here, and here we have this slope 1 for benzoic acid, and here we have sigma for the constants here that are for the different substituted benzoic acid. Notice again that because we have negative values here, this is 0 right in the middle, negative values are here, so these are electron donating groups such as your amino methoxy. On this side, positive values. It's electron withdrawing groups such as your halogens and nitro group, the cyano group, for example. But the main take-home lesson here is that this slope is 1. Notice it's positive, and it's unity for benzoic acid. I'm emphasizing 1 for benzoic acid because for other reactions it may not be 1. For other reactions it may not be positive. And that's how we can tell that the mechanisms are different compared to that of benzoic acid. All right, so let's see why the slope is positive and and um, and 1. So first of all, here's the benzoic acid again. So benzoic acid, substituted benzoic acid here, X could be in the para position here or in the meta position. Okay, so if you measured all the equilibrium constants and made a plot, you will get a plot of +1 for the slope, which implies that, let's see what it implies. You can see here that for the ionization of benzoic acid, this proton leaves, and here it is, and it leaves behind these electrons here, which means that in the transition state, this oxygen here is partially negative in the transition state. Remember, the transition state here is a description of a reaction going from reactant to an intermediate or product. So here's the reaction, reactant neutral. This carbon here is going to a negative carbon and carboxylate anion. Therefore, in the transition state, this oxygen here is partially negative. Since it's partially negative, it is saying that electron withdrawing groups would stabilize that negative charge. That electron withdrawing groups would stabilize that negative charge. Makes sense because electrons want to be distributed. So if we have an NO2 back here, for example, it would pull the electrons over here and stabilize that transition state. If we had electron donating groups, those to the left of the plot, it would destabilize this transition state, because if you put, for example, an NO2 here, let's see if I can do it here, OCH3, for example, here, you can see that these electrons are donated to the ring and destabilize that transition state. So that's one of the important implications here, is that a positive slope implies that the transition state in the most important step of the reaction, rate determining step or the equilibrium, in that step, electron donating group will slow it down and electron withdrawing group will favor that reaction. Okay, let's apply this to a different reaction. So this is now the ester hydrolysis and not the equilibrium constant or the ionization of benzoic acid. As you can see here, this is an ester, KOH. It's a hydrolysis, so as you can imagine, this comes in here and this comes out to get ethanol and of course the carboxylate salt. So let us see if we can determine the mechanism of this reaction if given experimental results. Key here again is if given experimental information, can we determine the mechanism of this reaction? Let's see. So here is the experimental result. And of course, it's a linear free energy plot, as we have seen before. So, different substituent constants here, different substituents, and of course, these are the constants from that table plotted against the rate of hydrolysis. You can see here that the slope is positive 2.5. Slope is positive 2.5. Two important aspects here that we'll emphasize in a second. The slope is positive. Notice positive slope. Same positive slope that was obtained for the ionization of benzoic acid, which means that electron withdrawing group favor that equilibrium. This means the same thing. electron withdrawing group, such as the p-nitro group, favors this reaction. As you can see, this is a fast reaction here because this is the rate. So it's fast for p-nitro and slow, this is the rate here, for the p-methoxy. So in other words, it has the same effect as that of the ionization of benzoic acid. However, the slope here is much larger, means that it's more sensitive. So let's give you more details here. So just to summarize what I said earlier, a positive slope means that electron withdrawing groups facilitate this reaction, which also implies that electron donating groups will have the opposite effect on this reaction. Key again is a positive slope means that electron withdrawing group will favor this reaction. The other aspect here is the magnitude of the slope. You may recall for benzoic acid it was unity 1. So if it's greater than unity, it means that it is more sensitive to changes in substituent compared to benzoic acid. If it's between 0 and unity, it's not as sensitive. Okay, so let us see if we can apply this concept here. So here is the p-nitro group here, which is electron withdrawing. So it's pulling electrons from the ring and from this reaction site, which we know is electrophilic. So this is a partial positive already because of the 2 oxygens that are bonded to this carbon. But in addition, it has a phenyl ring with an electron withdrawing group. So in the rate determining step where the OH negative, which is nucleophilic and has electrons coming in here, you can see that it's favorable. So it produces here a partially negative transition state, which is stabilized by the nitro group. So it's very stable. Let's look at this one. So here we have the OCH3. So this is pushing electrons into the ring and eventually over here. So the bottom line is when the nucleophile comes in, it sees this electrophilic carbon here because of the 2 oxygens bonded to this carbon. But this substituent is donating electrons into this carbon here, making this attack less favorable. When it does attack, however, you can see that the transition state is partially negative. So therefore, this transition state here is less stable than this transition state here. Since this is the rate determining step for these 2 reactions here, you can imagine this forming a more stable transition state. This is a lower barrier, much faster than this one that has a higher barrier, which has a less stable transition state. So this reaction is much faster here than this one. Okay, so let's look here at the summary. So a slope of negative 2.5, I think this is positive. A slope of positive 2.5 for the hydrolysis of ester. I'll correct this in the PowerPoints that I'll post. So a positive slope here, this comes in. So this is the mechanism for the ester hydrolysis based on the experimental information that we just looked at. So the base comes in, kicks the electrons up here, and when they come back in, ester comes out, and here is our carboxylic acid. Of course, it's an acid, so in the presence of a base, you're going to get the salt. But these are all fast steps. So the mechanism implies, based on the linear free energy relationships, that this is the rate determining step. How do we know it's the rate determining step? Because by changing the substituents here, we can change the rate of the reaction, which implies that the transition state here is relatively stable based on the substituents or less stable. Okay, let's look at another one here. This is a reaction which has the opposite effect. So we don't have the plot here, but it's given. So we have this reaction. It's a substitution, bromine, and we have KSCN. You recall that K plus and SCN here is, of course, the nucleophile. So it's a substitution where the bromine comes off and the SCN substitute for that bromine right here. So the question is, what is the mechanism for this reaction? Does it occur in one step, or does it occur in two steps? Is there a carbocation intermediate? Is there a carboanion intermediate? Etc. Experimentally, the slope is negative. Note here, it's negative, not positive as before. So the slope here, rho, is negative 3.89. Two things. It's negative, which means the opposite for benzoic acid, which means that instead of a negative intermediate in the transition state for the rate determining step, it will be a positive. And notice the magnitude, 3.89, much larger than 1, which means that it's a very positive intermediate. So with that information, just based on this, just based on the magnitude of this number and the sign of that slope, here's a possible mechanism. In the rate determining step, the bromine leaves to form a carbocation, positive. So two things, this is positive, this is positive, and we get that information from the negative slope, which means here that electron donating group will stabilize that charge. So you'd expect the slope to look like this, where this is electron donating group, and over here is electron withdrawing group. And of course, this is the rate in that direction. So this is a fast reaction and a slow reaction. Fast because we have electron donating groups such as OCH3. So if you put an OCH3 here, you can see that these electrons will donate electrons to stabilize the positive charge here. And if you stabilize the positive charge, you have a stabilized transition state for the rate determining step, which means a faster reaction. So hopefully from this, you get the information that just by looking at the slope, the magnitude, and the sign, you can tell what type intermediates are formed in the rate determining step. Key here, rate determining step, because that RDS determines the overall rate of the reaction. Let's look at a couple more examples. So here is another example here. Benzyl chloride in the presence of sodium hydroxide and water. Notice this here is now Cl, not a good A leaving group as before, as the previous slide. So it's not going to leave readily to form the carbocation as we have seen in the previous slide. But Experimental, the row here is negative, which means that there's a positive species in the rate determining step. And here it is 0.3, which means it's not as sensitive here. Let's look at this one. Same benzyl chloride here, but now we have here sodium iodide. Different type nucleophile here compared to the OH here. Better nucleophile here. And here, however, notice again, the rho value here, it is positive, which means that we cannot invoke here a carbocation. Because if a carbocation were formed in the rate determining step, that slope would be negative. But that means that this is not a carbocation here, but more than likely a partial negative or a negative charge next to the benzene ring. So we can assume here that as this reaction proceeds in the transition state, this carbon here going to be partially negative or negative, but not positive. And of course, we can see here 0.8, it's not very sensitive as benzoic acid to changes in substituent. Let's see what the mechanism looks like, putting together this information. Mechanism here, rho value of negative forming a carbocation. So you can see here when this leaves, we have a carbocation here. So that means that it's negative. This is the rate determining step, the formation of a carbocation. Why is the number here not large as before? A very poor, a good leaving group, but not as good as the bromide, as we have seen. So it's not, it doesn't readily leave to form this carbocation. It's still pretty close here to this carbocation in the rate determining step. So that reduces the partial positive character. And of course, in the fast step here, we have the nucleophilic OH coming in and forming the product. So this is a classic SN1 reaction. You will recall from your organic course that an SN1 reaction, the important step is the step where the electrophile has the leaving group leaving, one molecule electrophile has the leaving group leaving, SN1, and in the fast step, the nucleophile comes in. Let's look at the other one. Okay, so this gives you a reaction profile for the SN1. So this is the transition state for the carbocation here. And of course, we have the slow step because this is very large. And this is the fast step here because this energy of activation is small, going from carbocation to product. Two steps for the SN1. It's called SN1 because it's unimolecular, just one molecule here. By the way, this should be reactant because it's just one molecule that's going from reactant to carbocation. Again, I'll get that fixed for the PowerPoints that I'll post. Let's look at the other reaction where this is positive. So if that's positive, that means that we cannot invoke here a carbocation intermediate. So what happens here is it is proposed, well, we can propose now that this nucleophilic iodide comes in while this is leaving. So you can see this is negative, and the nucleophile comes into this carbon here, creating here a partially negative transition state because the negative comes in and this is still here. So if you have here electron withdrawing group, it's going to stabilize this, which is opposite to if you have electron donating group, it will stabilize the carbocation, but this is opposite. So here we have a slope that's positive. So here we have here, this will be a negative. So electron, this is electron donating group will be slow. And over here, where we have electron withdrawing groups will be fast because it will take electrons into that electron withdrawing substituent. Again, this is your classic SN2, where the nucleophile and the electrophile, two molecules, bimolecular, come together in one step to create the product, the substituted product here. So that's called the SN2 mechanism. Notice again the slope is positive, which means that the transition state is in this case partially negative, because the nucleophile, which is negative, comes into this carbon while this is leaving. And of course the transition state here looks like this. One step, also called a concerted reaction. So here we have reactants, the electrophile and the nucleophile, coming together to form the transition state and onto product. So this gap here represents the energy of activation. So in this case here, as we'd say, since this is negative, electron withdrawing groups would favor it, electron donating groups would of course raise this, electron withdrawing group would of course lower this to make this a faster reaction. Okay, let's conclude by looking at another type, the same type reaction, but on the different reaction medium here. This is an ester. So we have two types of groups here, the methyl group and the ethyl group bonded to that ester. But notice this is in sulfuric acid, strongly acidic. We will see in a second that the linear free energy plots are different from what we have seen before. There is a change in slopes for one of these, a change in slopes. And that is very important, as we'll see, because it gives us some essential information about the mechanism. So let's look at the plot. So here it is. This is for the methyl group, negative slope all the way down. But for the ethyl R group, or on the ester that is, it has the same slope here, but then it changes. So as it goes from electron donating groups to electron withdrawing group, it changes to a positive slope. I can tell you from now, what that means is that for this reaction here, for the ethyl, there is a change in mechanism from electron donating group to electron withdrawing groups, a change in mechanism. Let's see if we can analyze this a bit more. This is negative, which means that for electron donating group, that favors the formation of a positive species. Positive, probably a carbocation. But as we go into more electron withdrawing groups, remember this is electron withdrawing groups, electron donating groups here. As we get into more electron withdrawing groups, it changes the mechanism. Changes mechanism where here it has a more negative intermediate for the rate determining step. So let's see if we can apply these experimental observations. So here we have the ester, H plus, of course, as you can expect, would protonate these electrons over here. So we have this coming over here to get that. Resonance stabilized here, so carbocation. So this carbocation here is stabilized by electron donating groups, which means that electron donating group makes it faster, which means that we have a negative slope here. So this would be the rate determining step because we have a carbon that's positive next to the ring. So we have here an OCH3, for example. It would stabilize that and of course make that a faster reaction because this is the rate determining step. Of course, these are all fast steps here. So let's look at this one. So here, if we have here again these electrons here attacking to that to create that, we have here, and now if this becomes the rate determining step, here the slope would be negative. Here the slope would be positive. because we have electrons coming into this carbon. So in other words, if we have now electron withdrawing groups here, it would make this reaction more favorable, and this now becomes the rate determining step. So it's different from this being the rate determining step compared to this being the rate determining step. Right? So for this being the rate determining step, electron donating groups favor this. For this being the rate determining step, because we're putting electron groups here, electron withdrawing groups will favor this step. Okay, let's just make sure we got it. So if we have here an OCH3, for example, this would favor this being the rate determining step because it will stabilize this species here, OCH3, right? But if this is the rate determining step here, it would prefer to have NO2, for example, because we have a nucleophile electrons attacking this carbon here. So we want this carbon to be even more positive. So those are the two different rate determining steps that are possible. So what happens here is, so the question now becomes, why does the rate determining step shifts from this step to this step based on the ethyl group versus the methyl group versus the ethyl group? One rationale is that because we have an ethyl group here, this ethyl group here can assist in stabilizing the positive charge a little more, so it prefers to maintain its positive character until the nucleophile comes in. Just a rationale for that. Whereas if you have a methyl group here, not electron releasing, remember it's just a CH3, so not electron releasing. So once you have this, this is not stabilized anymore, so this is the end of the reaction. So these are fast. And these are fast. This is fast. But once you have an ethyl group, this ethyl group can stabilize this positive charge a little more, so it can maintain its positive character a little more, so that these electrons can come in to attack here, making this the rate determining step. So again, I think this is the end of this lecture. Yeah. So again, what you should be able to take from this is, if given the linear free energy relationship data, such as, and it's typically in terms of the rho, the slope, and so the important aspect here is, what is the magnitude of the slope? And what is the sign of the slope? Equally important, what is the sign of the slope? If the sign of the slope is negative, it means that we have a positive species developed in the rate determining step, key rate determining step. If, of course, the slope is negative, here we have developed a positive species in the rate determining step. Let me just say that again. I think I got them mixed up. So if the rate is positive, it has a negative species developed in the rate determining step. Positive slope, negative intermediate. If the slope is negative, it means that it has a positive carbocation, for example, developed in the rate determining step. So that should give you an idea of what is the rate determining step for different reactions and what type species are developed in the rate determining step for different reactions. I know this is a lot, but take your time, go through it again, and see if we can apply these concepts to developing, proposing different mechanisms for reactions. Okay? Continue to study hard, and the next lecture will be on kinetic isotope effect. That's another method to determine the reaction mechanisms of different reactions. Okay?